So last unit, we talked about how to graph linear functions. That's not what I want to talk about today. I'm going to do something really different and weird, and I sort of want to talk about what is a graph. Not many teachers or not many classes talk about what is the shape that we see when we plot, y equals 3x plus 1. So I want to start off with just asking a question. I want you to give me two numbers, right? Give me two numbers where, and I'll make this an easy question, where one number is exactly one more the other.
6 and 7.
So for example, someone said 6 and 7. That fits. 7 is one more than 6. Right. So give me two numbers where one number is one more than the other. 6 and 7, 1 and 2, 3 and 4, 4 and 5. So I'm going to list these guys down. 9 and 10 would work. That satisfies. Let's just write it down in the same format so it's not all jumbled up. So I'll write the smaller number first and then the bigger number second. So I heard some people say 6 and 7 would work. I heard some people say 1 and 2 would work. I've heard people say 9 and 10 would work. 3 and 4 would work. 4 and 5 would work. Just do one more. 12 and 13, you guys are not that risky or adventurous. Let's dive into the negative worlds. How about negative 1 and 0 would work? 0 is one more than negative 1. So you guys agree that this is a fairly easy question to answer. Give me two numbers where one number is one more than the other. What we did when you guys gave me those pairs, 6 and 7, 1 and 2, we built relations. That's why I wrote them as a coordinates. That's how we represent relations with a coordinate pair. I'm going to do one more here, 2 and 3, just to complete the pattern. What I want to do is visualize this. Well, what do these points, they are points, we made them points, what do these points look like? So I'm not going to draw a giant tick mark, so sorry for those of you guys who gave me 9 and 10 and 12 and 13. I'm going to basically ignore those. Those are pretty big numbers. I'm going to stick with the smaller numbers. So let's just go ahead and see what this guy would look like on a coordinate plane. So let's see, 2, 3, 4, 5, 6, 7, 8. Looks like I can fit 8, so I'll go up to 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. I'm breaking the cardinal rule of not doing a square graph. But here's a 8 by 7 coordinate grid, and let's just plot it. 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. That's 6, 7. 1, 2. I can't fit 9, 10. Sorry. 3, 4. I can't fit 12, 13. Sorry. 4, 5. Negative 1, 0. 2, 3. Gee whiz. What does it look like is forming here? A line, right? Now, it's not a complete line because we only plotted 1, 2, 3, 4, 5, 6 points. But, we played it safe. We stuck with whole numbers. But doesn't 0.5 and 1.5 count? Isn't 1.5 one more than 0.5? Sure, we can do decimals. So all of these points here that I'm plotting satisfies the question. Ignore this outlier here because I can't make tally marks evenly. All of these points here satisfies the question. Give me two numbers where one number is one more than the other. Whether or not you were aware of it at all, we were answering this question. Give me two numbers, x and y, where one of those numbers, say y, is one more than the other number. That was the question you guys were answering. Y equals x plus 1. And obviously, we know how to graph that, right? Though the y-intercept is 1, so we start at y equals 1, and the slope here is a 1, so you go up 1 over 1. So if I were to continually answer this question, give you guys every single pairs of numbers where one number is exactly one more than the other, and you plot it, all of them. I mean, would you guys agree there's an infinite amount of answers to this question? All those infinite amount of answers will eventually, if you were to plot them, eventually will blend together, bless you, into what would look like one solid line. So that is what a graph really is. Now I'm doing this as an example, I'm using a linear function as an example, but when you graph absolute values, those V shapes, in the future, we're gonna graph quadratics, rationals, square root functions. A graph is nothing more than a collection of answers. A collection of answers to a particular question, or instead of a question, to a particular equation. So yes, graphs, that's something that our Algebra 1 teacher or our geometry teacher told us to do. It's just something we did. A graph is a shape, which is true. But for Algebra 2, this is sort of the idea that I want to take away. So this is the big takeaway that I want us to gather. A graph is a visual representation of the solution set. Now, solution set sounds like a fancy math term. It means exactly what it sounds like. It's a set or a group or a collection of solutions, of answers. A graph is a visual representation of the solution set of an equation. Right. So in Unit 1, or in Algebra 1, when your teacher said, hey, here's this line, y equals 1/2 x plus 3, graph it. Yes, you are graphing the line, but more importantly, the concept behind it, the idea behind it is, you are actually graphing every single possible answer you can imagine to that particular equation. So if I ask you this question, hey, solve y equals x plus 1. Well, first of all, that's a rather ridiculous question because there's an infinite amount of answers. But if I ask you, hey, give me one answer to y equals x plus 1, all of these points and more are valid responses. You could tell me, hey, Mr. Vo, 1, 2 is an answer. That is true. 3, 4 is an answer. That is true. And if, for whatever reason, maybe I'm being mean that day and I'm going, I don't believe you, right? Prove it to me. Well, the way you prove something is an answer, just plug it in, right? So, for example, 1, 2 is a solution to y equals x plus 1 because, in math, 3 dots, upside down pyramid is because. What would happen if I plug in those points? So remember, x is your 1, y is your 2. So we get 2 equals 1 plus 1. We get 2 equals 2, which is a true statement. So that's how you know it is a solution. When you plug it back in, it works. So the moral of the story, if I give you one equation that has multiple variables, now this is Algebra 2, we're not going to go too crazy, so we'll stick with 2 variables. If I give you one equation with 2 variables and I ask you to solve it, one way to solve it is to graph it. Because, again, this graph here, this line here, is every single solution to that equation. Well, what we're going to do today is not solve one equation. We're going to solve 2 equations at the same time. Now, that sounds very difficult. Geez, Mr. Vo, I have enough trouble solving one problem. You want me to solve 2 problems at the same time? Well, what we're going to do is we're going to exploit this idea. If a graph is a visual representation of an equation solution set, if I want you to solve many equations at the same time, just graph it. Well, what would be the solution set to the entire system would be common solutions. Well, what would common solutions look like graphically? And this is the idea. If we can accept, and I hope we can, if we can accept a graph of an equation is its solution set, then if you graphed systems I think system should be singular. System of equations. If you graphed a system of equations on the same coordinate grid, coordinate, how do you spell coordinate? C-O-O-R
D-I-N.
Cartesian plane.
Yeah, Cartesian, but not coordinate.
Yeah. On the same Cartesian, I can't spell coordinate, but I can spell Cartesian. On the same coordinate plane, the solution, thank you very much, of the system, right, it should be a point that's a solution for both graphs. Well, if it's the same point for both graphs, that's what we call an intersection point. The solution of the system is the intersection points. Right. And I put the parentheses S there because, hey, your system could look all wonky, crazy with lots of squiggles and whatnot. They may intersect more than once. Now, for this unit, we're only, or at least at the very beginning, we're only going to stick with linear systems. So the good and bad thing is, well, do you guys want the good news or the bad news?
Good, bad.
The bad news is, since we're only going to stick with linear systems, I'm sort of babying you because there's only one of three possible situations. The good news is there's only one out of three possible situations, so there's not a lot of thinking. Have you guys ever played pickup sticks?
No.
No, it's a very old school game. Have you guys ever knocked over a little jar of toothpicks? Yeah. If you were to take a whole bunch of sticks or a jar of toothpicks and knock them over, it looks all messy and scrambled, but if you look at any two toothpicks, any two sticks, they really only fit into one of three categories. So, for any two lines, you have one of three possibilities. I drop two lines on the floor. They can randomly cross, right? And that's what usually happens. By some miracle, by some chance, two toothpicks, two lines could fall right parallel to each other. And even rarer, but still possible, you could have two toothpicks, two sticks, two whatever, fall right on top of each other. Okay. So, no, try it on your own. Go home, get a tub of toothpicks or sticks from the yard and dump it all over your house's floor, and don't blame me for it. But I can guarantee you that any two sticks, any two toothpicks will be one of these three categories. That's just how lines work with each other on a two-dimensional plane. Well, if we follow this idea, hey, solutions to systems are the intersection points. If lines intersect, how many times do they intersect? Once. So systems that look like the first picture, we would say have one solution. Systems that look like the middle picture, if solutions are intersection points and if your lines so happen to be parallel, how many times do they intersect? None. These would be the no solution situations. And if by some miracle your toothpicks landed right on top of each other, if you have two lines right on top of each other, they intersect everywhere, you have infinitely many solutions. It's as if you have one line, right? It's as if, I'm going to scroll up really quickly, but I'll scroll back down. If you have infinitely many solutions, it is as if I gave you one line. Say, for example, y equals x plus 1. And then if I asked you, hey, what's the answer to y equals x plus 1? You would say every single point on this line here. So if you had two lines that so happen to be right on top of each other, every single one of these points here would be a solution. Now, this is Algebra 2, so we got some fancy vocab words to talk about, and so let's go ahead and talk about them right now. So yes, you can say it's one solution, no solution, or infinitely many, but we want to sound fancy. This is Algebra 2 after all. Okay. So here's some vocab. A system that has at least one solution is said to be consistent. So at least one solution means consistent. A system that has no solution is said to be inconsistent. So no solution links with inconsistent. But there's further breakdowns than that. A consistent system with exactly one solution is said to be independent. Independent. So it's different than independent variable. We're talking about a completely different topic now, so don't get those mixed up. It's just a term we use for systems. So if you have exactly one solution, not two, not five, but exactly one, it's said to be independent. A consistent system with infinitely many solutions is, you guys can probably guess if you know your opposites, dependent. So infinitely many solutions is linked with dependent. So one thing I could ask you to do is I could give you a whole bunch of systems and ask you to classify them. Is it consistent? Is it inconsistent? If it is consistent, is it independent or dependent? Now, fortunately, you don't have a lot to memorize because, again, when it comes to linear systems, you have one of three choices. You could have an intersection choice, you can have a parallel choice, and you can have an coinciding choice. So I hope, based upon these definitions, the one solution choice is consistent and independent because it has exactly one solution. The parallel situation, it has no solution, so we consider him inconsistent. And then the coinciding choice, the infinitely many choice, because it has a solution, we say it's consistent, but since it's infinitely many, it's dependent. I'm just very lazy, so I'm using color coding. You guys understand what these colors mean, right?
Yeah.
Okay. If you want to go back and write the actual words, you can. I'm just feeling lazy and just using colors instead. Okie dokie? All right. So on the practice, you're going to have a whole bunch of questions that, they're going to give you just two systems, and they're going to ask you, hey, classify it. All you got to do is you figure out, hey, does it have an answer? Does it cross? Are they parallel? Or are they right on top of each other? Then you can just answer it accordingly. Since I don't want to leave the lesson without doing an example, let's just do one example together, just so we have something in our books. But in terms of concepts, in terms of ideas, that's it. That's all systems are. Systems are just more than one equation at a time, and one way to solve it is just to look at the graphs. The answers are where they cross. So for example here, suppose I ask you to solve x minus 2y equals 8 and y equals negative 3/4 x plus 1. That's all a system is. It's just multiple equations at the same time. So if I want to use this idea, hey, graphs are the visual representation of the solution set, let's look at all the answers by graphing. I want to graph these guys. So I'll make the first equation this color. I'll make the second equation this color. My third hour class said this color was annoying. Is that annoying to you?
No.
Okay. They said it was too bright or something. All right. Okay. So let's go back to Unit 1, graphing lines. Notice the first equation's in standard form. Graphing is a lot easier when it's in slope-intercept form. So for this line here, let's go ahead and solve for y, which I hope is not too hard of a challenge. Subtracting the x from both sides, give us negative 2y equals negative x plus 8. And then dividing out the negative 2 gives me y equals a positive 1/2 x minus 4. Right. The other equation is already in slope-intercept form, so I don't have to do anything. Let's just go ahead and graph this guy. I'm also hoping that my mental math is correct, because I sort of made this example off on the top of my head. So crossing our fingers, we get an integer solution. Okay. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Obviously, if I was doing this as homework, I'd probably use graph paper. So let's plot the blue function. So the y-intercept is negative 4. So I'm going to start down here at negative 4. And my slope is 1/2. So you go up 1, right 2. Up 1, right 2. Up 1, right 2. So on and so forth. What color is this? Orange, the orange line. The y-intercept is plus 1, so I start at the 1 here. And my slope is negative 3/4, so you go down 3 over 4. Down 3, 1, 2, 3 over 4, 1, 2, 3, 4. Down 3, 1, 2, 3 over 4, 1, 2, 3, 4, somewhere over here. There we go. So conceptually speaking, all of the green, everything that's orange, sorry, not green, everything that's orange is the answer to the orange equation. Everything that's blue is the answer to the blue equation. If I want to solve a system, I want to find answers that fit into both equations. It sort of makes sense to look at points that are both blue and orange. And visually speaking, there's only one point. This point here. What is this point located? 4 comma, I think it's negative 2. 4 comma negative 2. There's your answer, 4 comma negative. Now, we had some arguments. Mr. Vo, does that look like negative 1? Does that look like negative 2? You can always check your answers by substituting into both equations, because if this is a legitimate solution, it should work for both. So if I want to check 4 comma negative 2, you can plug into any of the formats, the standard form or the slope-intercept form. It doesn't really matter. I'm going to plug into the slope-intercept form since it's there. So let's check for the blue. So we have y, which is negative 2, equals 1/2, which is the x, minus 4. Negative 2 equals 2 minus 4. Negative 2 equals negative 2. So it works for the blue. Let's check the orange. Oh, I didn't know I could do that. Let's check the orange. So all you're going to do is plug the 4, negative 2 into the orange equation here. So that's y, which is negative 2, equals negative 3/4. The x is a 4 plus 1. Negative 2 equals negative 3 plus 1. Negative 2 equals negative 2. So indeed, it is a solution for both. So I know that my answer is 4 comma negative 2. Solutions to systems are going to be points. So please write your answer as a coordinate. I've had students write, oh, my answer is x equals 4 and y equals negative 2. Technically, it sounds like you're giving me two different values. It should just be one relation as an answer. So please write your answers for systems as points. Okie dokie. Right. Oh, bonus. You guys have your vocab words in front of you. I don't want to scroll up. Describe the system. Is he consistent or inconsistent? He's consistent because he has an answer. Is he independent or dependent? Independent. Independent because he only has one solution. So consistent and independent. if the question asks classify, this would be an answer. I just added it on as a bonus, but you will have some questions I'll ask to classify. Any other questions? That's it. Starting off, hopefully on a smooth note. That's 3.1. Graphs of systems of equations. The main idea, the main takeaway, graphs are visual representations of solutions. So if I want to solve more than one equation, just put all the graphs together and look to see where they cross.